So we need to talk about some metrics when looking at a chromatogram and how we use those to assess separation efficiency. And it doesn't matter what type of chromatography you're doing, whether it's ion chromatography or HPLC or gas chromatography or whatever, all of these metrics are universal. So the first one is this thing called retention time. And retention time just describes generically how long a compound is retained on the column or on the stationary phase from the point that you inject the entire sample onto the column. And so that's denoted here by this TR metric. TR is the retention time, and so you can see that's measured from the point at which you inject the sample to the point at which it's detected. And then we also have this adjusted version. The adjusted retention time is just the time that it takes for your each peak, in this case we're talking about the unknown here. It's the time that it takes for that thing to elute off the column from the point that the solvent first starts to show up. So if you've got a mobile phase and you put that on the column, how long does that take to elute? Usually that elutes off first. That's one of the first things you see, and so that adjusted time comes from the original retention time and then subtracting out the time that it took for the mobile phase, or the T sub m in this case. And we can define this thing called the retention factor. This isn't super helpful in that it's not a very practical thing to always compute, but it's just it gives us a sense for how long something is going to be retained on the column, and it normalizes that for any type of column here, because you're taking and you're computing the adjusted retention time here, T prime R, and then dividing that again by the time that it took the mobile phase. So you're normalizing it to the mobile phase time, and for that reason then this retention factor K can be extended across different columns, etc. And it gives you a mark for how long a particular compound is going to stick to your column and whether or not it's going to be separable from other things, because really the K is telling you how well, in some proxy way, how well those two things may stick and if they're be differentiable in a chromatogram. We have a better definition of that, which we call resolution, which I'll talk about here in a second. So resolution is the primary metric for separation efficiency. It takes into account two different characteristics of the peaks in a chromatogram, or two adjacent peaks. And really the simplest way for you to think about resolution is just if you've got a compound and it elutes and you have a peak here, and then you have another one that comes right after it, are these two things different and differentiable? Or do you have something that looks like this and you're not really sure, is that made up of two different peaks that just have such similar chemistry or physical traits, at least based on the type of chromatography you're running, that they're undifferentiable. So resolution, or the ability to resolve something, is the capacity to actually tell the difference between 2 points. Of course, tell the difference is a qualitative or a subjective metric, and so there's several different ways that we can do that. And so I took from your book the definition of resolution here. There's sort of 3 different ways that we can think about that. The first of which would be the difference between the actual retention times, so this being the retention time at each one of these points, so delta TR divided by the average width of these two peaks, and that those widths are defined as the distance here and the distance here, and so that average width. So you're really sort of getting a measure of like how far they are apart, and then how wide are they at the base, and that gives us a sense for whether or not these things are resolved. The other one that I find to be helpful, this one is not really relevant or useful, but this one is an empirically useful one because it's easy to compute. What this is a value where it's more practical to use, because instead of measuring the average width of both peaks at the base, that can be really hard if you have a system that looks like this picture here, because in this picture you can see it's not easy to actually measure the base because you really only have the blue line to look at, and so you have clearly not fully resolved those two compounds, whatever method of separation you're using. In that case, it's difficult to figure out where to measure the base, right? The sort of invisible underlying peaks are shown here in dotted lines, so you'd be measuring from here to here to get W of the first peak, and from here to here to get W of the second peak. That's not easy to do, although I will say that there are fitting programs out there where you can take a peak that's almost superimposed like this and actually fit these two underlying peaks if you know the type of distribution. In this case, these are Gaussian type distributions, as dictated by the type of broadening that actually dictates the width of a peak. We'll talk about that in a little bit. Anyway, this metric, W sub 1/2 AV, is actually the average at full width at half max. And so what that means is full width at half max means the full width of a peak, in this case, like from here to here, at half of the maximum value. So if you have a maximum value that's here, 1/2 of the maximum would be here, and we would measure then the width of our peak from those 2 points. So we call that full width half max, or FWHM. The utility in that is a little bit easier to predict or see the full width at half max, even if you don't have what's called baseline resolution. Baseline resolution meaning that the peak comes all the way down to your x-axis before going back up again. So this fourth picture down here has what we'd consider baseline resolution, where we've totally resolved these two peaks, no question about it. So the resolution here, you can see this is a measure of 1, this is a measure of 0.75, this is a measure of 0.5, where we really just have the widths of these peaks blurring completely together, and we have no difference in the peaks at all. So this is our primary metric for separation efficiency. As you can imagine, if you've got a whole bunch of peaks being eluted, how well can we separate those peaks? This is the metric that we're looking for. The larger the resolution value, especially if it exceeds 1.5, that says we have baseline resolution, which isn't always necessary. Resolution of 1 is great, and that's going to be good enough for us to quantitate off of. Resolution of 0.75 and less becomes a little bit tricky because some inferences have to be made about the contribution of different compounds to those peaks. So let's compute a quick example. Let's use the latter expression here, just because I find this to be one of the most useful in a practical sense. So you've got sort of generic chromatogram, doesn't matter its origin or what contributed to this. You got 2 peaks and you want to compute the resolution of these 2 peaks. On your x-axis you have time in seconds, and then I just labeled the actual retention time for each of the peaks A and B. So you got 407 seconds and 424 seconds for these 2 peaks. And then I also just threw up, although you should feel confident that you could measure these easily, right? You would just look down at the axis here and then look at what each of those values are. And then I have W half, which remember is the full width at half max. So that was measured from here to here and here to here in blue for each of these peaks. So if we wanted to compute the resolution for this, you would take this 0.589 value, which just comes from the statistical distribution of these 2 peak shapes, times delta retention time. So that would be times 424 minus 407 divided by the average of those 2, which would be 17 plus 9.4 over 2. If we compute this, we get a value of 1.18, which tells us that our separation is between those 2 compounds is pretty good. Remember, 1.5 is baseline resolution. So these things aren't quite baseline. So you would have an extension of this tail down to here, and you'd have an extension of this tail down to here, but they're resolved well enough that they're 2 distinct components or peaks.